In this video, we are going to discuss about address sequencing, or can also be called as microprogram sequencer. Generally, we will design control unit by using two approaches. The first approach is hardwired control unit. The second approach is microprogrammed control unit. Here we are going to discuss about microprogrammed control unit. In microprogrammed control unit, the control logic is implemented with the help of a software, a program. So that microprogram is stored in control memory. So control memory contains the microprogram, which is useful for executing the control unit. Next, every microprogram contains a collection of micro instructions, and each micro instruction contains one or more micro operations. So what is control memory here? Control memory stores microprogram. Microprogram contains a collection of micro instructions, and micro instruction contains a collection of micro operations. So that's why here we have written micro operations here. So while CPU is executing the current instruction address, then we have to generate the next instruction address. So those two should be done simultaneously. So while the CPU is executing the first instruction, then how we can generate the next instruction address? So that is nothing but the concept, address sequencing. So how we can generate the next instruction address. Sequence means how we will get the next instruction address, or microprogram sequencer. So the duty of microprogram sequencer is to generate the next micro instruction address. Okay, here there are four approaches are there. The first approach is incrementing control address register by 1. Here we have control address register. Control address register contains address of micro instruction that is to be stored in the control memory. Okay, so let we have a control memory like this. So let the first instruction is 000. Let the data of this instruction is 1010 like that. Let the second instruction address is 001, whereas let the data is like this 01101 like that. So control address register contains the instruction. What is the micro instruction address here? This 000. So control address register contains the micro instruction address that is to be stored in the control memory. Okay, so here the first approach is incrementing control address register by 1. So for that purpose here we are using an incrementer circuit. So incrementer circuit increments control address register by 1. So what is the previous value in control address register? 000. If we increment 000 by 1, then the output is 001. So now with the help of the multiplexer, we know about the multiplexer. Okay, so multiplexer accepts that value and it will transfer that value to control address register. So once incrementation is over, then the multiplexer transfers 001 to the control address register. So now the next instruction address will become 001. So that is the first approach, incrementing control address register by 1. And now let's see the second approach. The second approach is subroutine call and return. Subroutine register. We know what is a subroutine. Subroutine is nothing but a function that we use in C, C++ and Java, any programming language. A subroutine contains a collection of instructions which are useful in order to perform a specific task. Mainly we use a subroutine for the repetition purpose. So here we know that whenever a function is called, then the control goes to the function definition. All the statements in the function definition will be executed. Once the execution is over, then the control comes to the next statement of the main program. So that next statement will be stored in subroutine register. Let in the main program we are at the address 4500. So what is the next instruction? 4501. So this 4501 will be stored in subroutine register. After that the control goes to the subroutine. So all the statements in the subroutine will be executed, and after that, based upon this subroutine register value, control address register will be generated. Okay. Here what is the subroutine register here? 4501. So multiplexer transfers that 4501 to the control address register. So now 4501 instruction will be executed now. So let it be some 4501 instruction address. So now this instruction will get executed. So this is the second way, using subroutine register. Now let's see the third way. Third way is unconditional. The third way is unconditional or conditional branch. So what is the third way? Unconditional or conditional branch based upon the status bits. So first let's see about unconditional branch. Unconditional means the name itself specifies the meaning. Unconditional means without checking the condition, the corresponding address will be loaded into the control address register. So let us assume that here we have an address like this. Let the CPU is executing 001, whereas here let the address is like this, 111 is the address. If it is unconditional address, then what will happen is, without checking any condition, here the condition won't be checked here. What is the branch address here? 111. So this 111 will be transferred to the control address register with the help of the multiplexer. Okay. So here what is the branch address? 111. So without checking any condition, this 111 will be transferred to the control address register with the help of the multiplexer. Now the control address register contains 111. So now the instruction at the address 111 will get executed. This is about unconditional. Unconditional means there is no need to check any condition. Directly we can jump. And the next one is conditional branch. Conditional branch means we have to check the condition. Whenever the condition is satisfied, then only we have to load that address into the control address register. Here, for that purpose, here we have to select the status bit. Here the branch logic, check the status bit. There are several status bits are there, like 0 flag, sign bit flag, overflow flag. Likewise, there are several bits are there. Let us assume that now the flag is for 0 flag. So we need to check whether the result is 0 or not. Here let the result is 0, whereas let the instruction address is something like this, 1010. Let the instruction address is like this. Okay. So the branch logic will checks whether here the content is 0 or not. So here we have content as 0. So what generally control memory contains what? Some micro instruction. In micro instruction we will have some conditional bits, conditional bit, branch bit, status bit. Likewise we will have several bits in the micro instruction. And let the condition bit is 000 here. So this 000 will be checked here. So here the condition bit is 0 only. So very good, the condition is satisfied. So this address, this 1010 address will be loaded into the control address register with the help of the multiplexer. So this is about conditional branch based upon the status bits. So branch logic, here we have branch logic. Branch logic will check whether that status condition is met or not. If that status condition is satisfied, then only the corresponding address will be loaded into the control address register. Suppose if the condition is false, let the content is 001 here, but we are checking for 0 flag here. So we can say that this is false. In that occasion, increments control address register by 1. So the next instruction address will be executed. So this is the third approach. Now let's see the fourth approach. Here the fourth approach is external mapping the instruction. Fourth approach is mapping instruction. So for that purpose here we are using some instruction register. Let us assume that this is our instruction register. So the first 4 bits are some 1011 and this is nothing but some address field. Here we will do some mapping here on opcode. This is nothing but opcode operation which we are performing. So on this opcode we will do some mapping. So on those 4 bits we will do some mapping. So that's why I am using some don't cases. This access specifies that we are doing some mapping here. Here the mapping is add 10 to the left side and add 2 zeros to the right side. This is our mapping. It is our choice. We need to generate some instruction address. That's it. So 0. So we need to copy these 4 bits here, 1011, and we are appending these 2 zeros here. So the next instruction address is this address 0101100. So this address will be, so here we have mapping logic. So this is nothing but mapping logic. Mapping logic means here the mapping logic is append 10 at the left side, 2 zeros at the right side, and copy the opcode bits as it is. Okay, this is the mapping logic. So then after that multiplexer transfers the corresponding address to control address register. So now the instruction at this address will get executed. Okay, so in this way we can generate the next instruction address while its previous instruction is executing. So this is about address sequencing or microprogram sequencer. In the next video we will discuss about the remaining.